right. Hi, everybody. My name is Lindsay Moyer, and I am from Kutztown University in Pennsylvania. I am so excited today to be here to present to you part of my honors thesis, which is the composition of magic squares. Today, we'll be talking about the history of magic squares, along with the three main types of compositions, which are the Siamese, singly even, and doubly even methods, and then two main types of magic squares, which were created by Benson and Jacobi, or the concentric and pandiagonal, along with my reference page. The magic squares originated with the legend of Lo Shu. This is one of the oldest known number mysteries found in the book entitled Yi King. Legend goes that each year the king would make sacrifices to the river god for the flooded river. And then one year a turtle came onto the land. On its shell it had dots, and each row, column, and diagonal of dots added up to the number of 15. This is the number of the cycles in the 24 cycles of the Chinese solar year. After that, the king decided to give 15 sacrifices per year. This turtle became known as the divine turtle and is the oldest example of a magic square, which is over 3,000 years old. I keep saying magic square, but what is a magic square? It's an n by n square, meaning it has the same number of rows and columns. The cells are filled with the numbers 1 through n squared. As you can see, each row, column, and diagonal has to add up to the same number. In this 3 by 3, they all add up to 15. This number is called the magic constant and is found with the formula n times n squared plus 1 all divided by 2. Our n variable is going to be found by whatever our n by n square is. So if you're doing a 3 by 3, our n value is 3, also known as the order. The first method we're going to talk about is the Siamese method. This is used for creating an n by n magic square using the numbers 1 through n squared, where n is going to be odd. To start any method off, you want to start by doing the magic constant. We're going to do a 5 by 5 as our example. So you plug 5 in for n, and you get 5 times 5 squared plus 1, all divided by 2, meaning that each row, column, and diagonal has to equal a number of 65. How do we do that? So we're going to use our Siamese method, which is you're going to start in the top row, in the middle column, and place the number 1. You're going to do this next step n amount of times. The step is you go to the right one column and up one row and place the next consecutive number there. However, if you see, that would put 2 floating above our magic square. When this occurs, we do a wraparound, staying in the same column but going to the bottommost row and placing our number there. You see, doing this step again, we place our 3, but if we do the step one more time, 4 will be floating on the right side of the magic square. So this time we do a wraparound again, staying in the same row, but moving to the leftmost column and placing our number there. And then we do the step again to get 5. However, when you do the step one more time, we get back to our cell that's already filled in with 1. When that occurs, you go to the last number placed, go to the cell below that, and put the next consecutive number there. So we place 6 below 5, and then do our step 5 more times until we get back to our occupied cell of 6. Then we place our 11 right below 10. Now it's interesting to note, when you make a square using the Siamese method, our main diagonal is always going to be consecutive numbers. In this case, we have 11, 12, 13, 14, and 15 for our main diagonal. We do this step 2 more times to complete our 5 by 5 magic square, because now each row, column, and diagonal equals our magic constant of 65. This is how the Siamese method is used. Our next method is going to be a singly even method. This is now when n is singly even. So this means that n is going to equal 4m plus 2, where m is the member of integers positive. So basically it means n can be divisible by 2, but not 4. Numbers such as this are 6, 10, 14, etc. For our example, I'm going to be showing you a 10 by 10 because a 6 by 6 does not use all the steps for the singly even method. Our first step is to find the magic constant. We plug 10 into our formula and get that each row, column, and diagonal has to equal 505. To start with this method, we're going to make 4 mini magic squares, or 4 quadrants. The dimensions for each quadrant is going to be n over 2 by n over 2. Plug in 10 in, we get that each quadrant is going to have a dimension of a 5 by 5. You label it top left A, top right C, bottom left D, and bottom right B. I've color coded them so we can easily see the different quadrants. Now we have to see what numbers go in these. We use the formula n squared divided by 4. Plug in 10 in, we get that each quadrant has 25 numbers. The first 25 are going to go to A, the next to B, next to C, and the last 25 get assigned to D. But now we have to look, how do we place these numbers in our magic square? We treat each quadrant like its own 5x5 magic square, and we use the Siamese method on each. So A is going to look identical to the one we just produced in the last section. B is similar, except instead of starting with 1, we're going to start with the number 26 and go from there. C, we start with 51, and D, we start with 76. So you can see here, we have 4 different magic squares in each quadrant with the Siamese method. However, not all rows, columns, and diagonals do equal the magic constant yet. So we have to make highlighted areas. It's going to be an A1, A2, A3, D1, D2, D3, a C1, and a B1. So these are what they look like, and this is how we find them. So to create A1, you go to the top row in A, and you highlight the number of columns until you hit the middle column. So we highlighted 2. You have to make it n by n out of that. So we created 2 by 2 for A1. You move to the row directly below A1. We go in 1 column and then highlight the same number of columns as we did in A1. A3 is a replica of A1 except in the bottom left-hand corner. And then D1, D2, and D3 are replicas of A1, A2, and A3 except in the D quadrant. And then for C and B, this is the reason why I've showed a 10 by 10 and not a 6 by 6. So to find C and B, you highlight 1 less column than you did in A. The entire column is C and B. So you see in A, we highlighted 2, causing us to highlight 2 minus 1, so the entire 1 cell in C and B. However, for a 6 by 6, you only highlight 1 cell in A, so 1 minus 1 is 0, causing you not to have any C or B highlights. But I wanted to demonstrate all the highlights for this example. Now what we do is we're going to swap all the cells in A1 with D1, A2 with D2, A3 with D3, and C1 with B1. This is shown on this slide. You can see now we have the lighter highlights on the top and the darker highlights are now on the bottom of our magic square. This is actually our finalized 10 by 10 magic square and how the singly even method is always done. Now the last method we're going to discuss is a doubly even method. So this is now where n is going to be doubly even. So this means n equals 4m, where m is a member of the integers positive. So now n can be divisible by 2 and 4. Examples of this are 4, 8, 12, etc. So starting off, once again, we plug 8 into our magic constant to get 260. So for this, the first step is to now make corner highlights. Those dimensions are n divided by 4 by n divided by 4. So we're going to plug 8 in to get 4 corner highlights of 2 by 2s. We then make our main highlight. That is going to have dimensions n over 2 by n over 2. So we're going to have a 4 by 4. The main highlight, if you see, connects the corner highlights but never overlaps the corner highlights. But now we have to think, how are we going to plug numbers into this? What we do is we start in the top left cell with the number 1. We count consecutively from left to right and then move to the next row, left to right, and so forth, all the way down to the bottom right-hand cell. What we do is we only fill the numbers in when it's the highlighted cell. So you can see here, the top row should read 1, 2, 3, 4, 5, 6, 7, and 8. However, we don't fill in the 3, 4, 5, and 6 because they're not highlighted cells. But now we have to think, well, how do we fill out these non-highlighted cells? We're going to start back at 1, but this time we're going to start counting with 64. We count backwards with the same process all the way down to 1, but this time we fill in the squares that are not highlighted. So if you see, the first row would read 64, 63, 62, 61, 60, 59, 58, and 57, but 64 and 63 and 58 and 57 are not going to be filled in because those cells are already highlighted and occupied. This is the doubly even process, and this is how our 8 by 8 magic square is formed. So our next main magic square that we're going to talk about is the concentric or bordered magic square. This was created by Benson and Jacoby in their Magic Squares book, which I'll reference at the end. So this magic square is going to remain magic if the borders which consist of the top and bottom rows and the right-hand and left-hand columns are going to be removed. So if you look at this magic square I have an example of, if you remove all the red cells, our white cells are still going to remain magic. However, it's not going to be a normal magic square because we're not going to be using numbers 1 through n squared. To find these, there's 3 different types. We're going to have an odd, singly even, and doubly even once again. But for time for today's presentation, I'm only going to show you the odd way, but I have studied all the ways. The difference with the singly even is you're going to be using a set C and set D, and then for doubly even, you use a set E and set F, and the corner values are always going to be different. And whatever you start with is going to be different. So for an odd, we're going to create a 5 by 5. We're going to start with the original odd order magic square plus 2 times n minus 1. Original odd order means the odd number previous to a 5 by 5. So we start with a 3 by 3, and then we're going to add 2 times n minus 1. Now, n is going to represent what you're trying to find. So we want a 5 by 5, so n is going to be 5. That means we start with a magic constant of 15, but add an 8 to each cell. We now get a magic constant of 39. We take this 3 by 3 and put it in our main 5 by 5. And you see for a 5 by 5, we're going to need a magic constant of 65. This means we have to add 26 to each row, column, and diagonal. To do this, we're going to use complement pairs. They are two numbers that are added together to always equal a desired value. In our case, it's going to be 26. We had 16 cells left, so we're going to have 8 complement pairs. Our numbers we had left were 1 through 8 and 18 through 25. So I've paired them together so each pair equals the desired number of 26. I colored them so we can see how the complement pairs live in our final 5 by 5. To start off, we plug in our n value into our 4 corners to get the top left cell of 23 to be the complement pair to the bottom right cell of 3, and the top right cell of 19 to be the complement pair for the bottom left cell of 7. We're going to plug these numbers into our main 5 by 5, and you can see with the colors that the complement pairs live on the diagonals. Now we're going to have to fill out set A and set B. So these sets are given to us, and you start with the first row of n, and then n squared minus a, n plus a, as many rows as you need. And then set B is n squared minus a prime, n plus a prime, as many rows as you're going to need. If you notice for set A, we're going to need 3 numbers, and same with set B. So we're going to need the variables a and a prime. To get the values for this, we're going to use 1 through n minus 2, so 1 through 3. However, we can't use the value in the corners, which is n minus 1 divided by 2, so we can't use 2. So I designated a to be 1 and a prime to be 3. Plug in our variables and our n value into set A and set B. We get set A values and their complements, and then set B and their complements. We then plug these into our main 5 by 5, with set A being in the leftmost column, the complements in the rightmost column, and then set B being in the bottom row and the complements in the top row. You can notice here how all the complement pairs do live in the same row, column, and diagonal, causing us to now have our 5 by 5 concentric odd magic square. And like I said, the singly even and doubly even methods are produced in similar fashions. Our last main type of magic square is going to be the pan-diagonal magic square. So it has all the same properties. It uses 1 through n squared, and each row, column, and diagonal adds up to the magic constant. However, now, the diagonals that wrap around the edges of the square are also going to equal the magic constant. So when you look at this, all the blue cells equal the magic constant, as well as the pink, green, and orange cells. How do we find this? We're going to create a 4 by 4. So what you start with is a primary square. The dimension for this primary square are n over 2 by n over 2. So we're going to start with a 2 by 2. In each cell, we're going to put a v comma w. V is going to represent our tens place, w is going to represent our units place, and v comma w is going to equal vn plus w. But how do we fill these cells in? So we follow 5 requirements. Requirement A is going to be that each of the n squared divided by 4 possible combinations of plus or minus 0, plus or minus 1, all the way to plus or minus n over 2 minus 1 have to be in the tens place and in the units place, but can appear once and only once. So if you have a plus 3 negative 1, then you can have plus 3 plus 1, negative 3 negative 1, or negative 3 plus 1. Also, requirement B is that each row has to contain n divided by 4 positive and negative units. And the requirement C is that each column has to contain n divided by 4 positive and negative tens. D is the sum of the units in each row has to equal 0. And E is the sum of the tens in each column has to equal 0. So we're going to break it down and just start with A. So you see, plug an n in, we have to get 4 possible combinations of 0 and 1. Our combinations are going to be 0, 0, 1, 1, 1, 0, and 0, 1. But now how do we put them in our primary square? So we're going to look, and D and E say the sum of the units in the row and the sum of the tens in the column has to equal 0. The only way to get this is to put the +1 and -1 together and the +0 and -0 together. Also, we know the units in the row and the tens in the column have to have a positive and negative sign. I started with the +1 in the top left corner and then filled everything out from there. However, the primary square is not unique, so you could have placed that wherever you want it in whatever cell. Our next step is going to be to use this generating square. This is given to us and is always unique. So what we're going to do is we're going to place the primary square in each quarter of the main square according to the instructions of this generating square. So the top left cell is positive, positive. That means we're just going to replace our primary square in our main square. Our top right is a negative in the tens place. So that means we're going to flip all the signs in the primary square in the tens column and then replace the primary square. Our bottom left-hand cell is a negative in the units. So we're going to switch all the unit signs in the primary square and then place that in our main. And then we have a negative, negative. So we're going to switch all the tens and the unit signs and then place that primary square in our main 4x4. We are now going to add n-1 to each negative number. So add 3 to -0 to get 3 and 3 to -1 to get 2. We're going to take these ordered pairs and we're going to plug them into our formula of Vn plus W. Those new answers are going to go into each cell, but if you see one of our cells have 0, which we can't have, so our last step is to add 1 to each cell. We now actually have a full pan-diagonal, and to just show that it works, I've added up all the pink, blue, orange, and green cells, and you can see that all of them do equal the 34, which is our magic constant for a 4x4. And then here is my reference page. And most of my work for this section of my thesis came from the new recreations with the magic squares from Benson and Jacobi. Thank you so much for listening.
Thank you so much, Lindsay. We've got one question. What sort of ideas from linear algebra and number theory are at play behind the scenes of these concepts, assuming there are connections?
That's actually interesting. For my main project, I did composition, properties, and linear algebra. So I have a whole section in my thesis on linear algebra. And there's a lot of dot products that go into it, a lot of determinants. It's actually very fascinating when you look in depth at it. And I can easily show whoever that question was, everything I've done with that section. So.
Thank you again. We've got one more minute. If there's any other questions, feel free to drop them in the Q&A section or the chat. All right, looks like Gabe was the one who asked the question. He just dropped that in the chat. All righty, if there's no further questions, we will move on to our next student presenter. Thank you again, Lindsay. Next up is Anthony Clacken with Iowa Gamma. Anthony, if you want to go ahead and share your screen.
Can everybody hear me?
Yep, we can hear you and we see your slides.
All right, sounds good. So I'm going to be giving a talk about forbidden posets for a class of interval orders. I'd like to thank Dr. Keller for inviting me to participate in this research. It's been a lot of fun, and it's been, as I'm sure any of you who have done proof-based work know, it's been very frustrating, but very rewarding as well. And so I'm going to start by defining just a few of the important terms that I'd like you guys to be familiar with or refamiliarize yourself with so that I can go through the actual research itself. The first term is poset, and the question being, what is a poset? It is short for a partially ordered set. We're going to define it as a set of objects, which we're going to call X, keeping in mind that the X is the set of objects and not a particular object. And these objects are either going to be comparable, for which we'll use a less than or equal to sign or a less than sign, or they're incomparable, for which we have the double bars under some given relation. And the notation we're going to use for this, you can see at the bottom of the screen here, is P equal to the set X under this given relation. I do want to point out here that the relation is not necessarily less than or equal to. It's not necessarily less than, and we'll see an example of that on the next slide, what I mean by that. So our example that we're going to use to get something concrete in your mind is to consider the set of integers from 1 to 8, and the relation will be divides. So we're still going to use the less than sign, but in this case, we will read it as divides. An important definition to keep in mind right here is transitivity, which is if A divides B and B divides C, then we know that A divides C. And so we're going to list out our comparabilities here, and keep in mind that any relationship that's not listed here is an incomparability. So for instance, you see that 1 is comparable to 2, 3, 4, 5, 6, 7, 8. 2 is comparable to 4, 6, and 8, and so on and so forth. And again, we would read this as 2 divides 6. And as I said about the incomparabilities, we do not have 2 does not divide 3, and therefore, if we were to write that, we would write 2, the 2 vertical bars, and then the 3. Now, the way we're going to represent this visually is on the right-hand side of the screen over here in this poset diagram that we've created. You'll see the notation down there is P equals the set of integers from 1 to 8 under this relation divides. And you can see, if you look at the lines that go between our nodes here, that they represent comparabilities. So for instance, 1 is comparable to 2, 2 is comparable to 4, and so on, whereas we do not have 2 comparable to 3. And this is where I want to draw your attention to transitivity. It's so important because it makes this actually something that we can look at and read. If we had to have a line between every single thing that was comparable, not using transitivity, it would make this a very confusing diagram to read. The second thing that I want to refamiliarize you with is intervals, and we're going to flash back to your high school pre-calc or calculus class and remind ourselves that there are 2 types of intervals that we're going to really consider when we're talking about these posets. The first are open intervals, which contain everything between the endpoints, but not the endpoints themselves. So for example, this is an open interval from 0 to 5. The square root of 2 is in there, pi is in there, 3 is in there, but what is not in there is 0, and what is not in there is 5. And the notation, as you've noticed, is going to be the interval for this X is represented with the open and closed parentheses. The other type of interval are closed, which are going to be the same as open intervals, except that they contain their own endpoints. So for example, the closed interval from 0 to 5 contains everything in the open interval from 0 to 5. It also contains 0 and 5. This is going to be really important when we talk about the interval representations of our posets. And the notation here, once again, we're going to look at the example and see that we use the brackets rather than the parentheses to represent closed intervals. So now I'm going to show you a little bit more about how we can go from the poset diagram we were talking about and represent it using intervals. So I want to draw your attention to A and Y for a second. You'll see we have this comparability arc in between A and Y, meaning that whatever relation we're using here, A is related to Y. If you look over here at the interval representation, you can see that the interval for Y is completely to the right of the interval for A. And so that is how, if you were given this interval representation, you could tell by the fact that these 2 intervals don't intersect that y should be related to a in your poset diagram. In a similar manner, you can look at x and y, which are obviously incomparable in this poset, and you'll see that those intervals actually do intersect each other. Right here, you'll see the interval for x is not completely to the left of the interval for y. So like I was saying earlier, if you were given this interval representation, you could look at this and say, okay, I know that the interval for x is not related to the interval for y. The interval for x is not related to the interval for a. I also want to draw your attention up here to the interval for b, which is incomparable to y, it's incomparable to c, and it's incomparable to d. And you'll see that the interval for b does indeed intersect the intervals for y, c, and d. So that's kind of how we would go between these two things and check how these two things go back and forth to each other. So now we're going to get into, now that we've got some background, the actual research. And the previous work that's been done are on things like unit closed interval orders. Now, unit obviously meaning length 1 in this case in the traditional sense, and closed meaning when we represent these using the intervals that you saw on the previous slide, the intervals are only going to be allowed to be closed. And we call this unit closed interval orders. That is a specific class of interval orders. So unit closed is the class here. And within each class of interval orders, we have what we call forbidden posets. And that pretty much just means that these are posets that cannot be represented using these interval orders, using this class of interval orders, I should say. For instance, for unit closed interval orders, we have a 2 plus 2, which you'll see here in the figure on the left, and a 3 plus 1, which is this y, x, w, and z. Neither of those can be represented using unit closed interval orders. And we're not necessarily going to go into why they can't be represented because of time constraints. Other research that's been done before this are on other classes of interval orders. We have the unit open closed interval orders. Again, these are length 1 intervals, and the intervals in this case can be either open or closed. So a team worked on finding the forbidden posets for that class of interval orders. And then a separate team worked on what we call 0-1 closed interval orders. And those can have length 0 or length 1, but all the intervals are closed in the representation. So this is really where the research that we've been doing starts. We've been considering a class called 0-1 open closed interval orders. And as you can probably infer from the previous slide, we're talking about our intervals are allowed to be length 0 or length 1, and they can be either open or they can be closed. The important thing that I want you to take from this slide is that a 3 plus 1 in this class of interval orders can be represented. And I will show you how we represent that. So let's say we have our 3 plus 1 here with nodes labeled A, B, C, and X. We represent this with these intervals on the right here. And you can see that the interval for B is open, which allows A and B to be put on either side of it. I also want to point out that these single points A and C are what we would define as a length 0 interval. So these are the technical results that we've discovered, and this has really been where the bulk of my work has come, is in the proofs and finding things out along these lines. The lemma 1 up here is what actually forces the interval representation for the 3 plus 1 that you saw in the previous slide. So it's important to note that the 3 plus 1 representation that I just showed you is forced by lemma 1. So it is the way to represent a 3 plus 1 in this class of interval orders. The corollary here talks about a 4 plus 1. If you'll picture the 3 plus 1, but just put one more node attached to the string of 3, the chain of 3, that is what a 4+1 is referring to. And the theorem 3 down here, the important notation are these D's and U's. D of X just means everything that is less than X if you use the traditional less than relationship. And U of X, on the other hand, is going to be everything greater than X. And so these are using subset arguments, and they will be used on the following slide. Both the corollary and the theorem will be emphasized on this slide. So those three important, the lemma, the corollary, and the theorem, give us this set of forbidden posets. And the corollary gives us these top four. You'll notice those have a similar look about them. You can see the 4+1 inside them with A, B, C, D, and X on each of those top four up here. And this one right here is the one that uses the D and U subset notation that we were talking about in theorem 3. And in every single one of these, we actually do use lemma 1, and I'm going to show you exactly how in the following slides. So all of these posets, along with something called the duals of these posets, which is basically just take this guy and flip him on his head, turn him upside down, and that is his duals. So all of these we have shown are forbidden for the class of 0, 1 OC interval orders. So I'm just going to walk you through not how we would technically prove these things, but sort of a visual representation of why we can't represent them using 0, 1 OC interval orders. So we're going to take this 3 plus 3 plus 1 here at the top of your screen, and we're just going to start by using A, M1, D, and X, and using the forced 3+1 representation that we showed on a previous slide. So remember that all of this is forced to be in that representation. And then we're going to put in the intervals for B and M2. So B is forced to be length 1 because B must be incomparable to both M1 and A. So as we saw earlier, to make it incomparable, it must intersect the intervals for both M1 and A. And because M1 is open, B must be greater than length 0 to intersect both A and M1. So it must be length 1. M2 is actually forced to be length 1 by the lemma 1 that we talked about earlier. You may have already spotted the problem that we're going to run into, which is where the heck are we supposed to place the interval for C? So C must be greater than M2. So the entire interval for C must be to the right of M2, but C must also be incomparable to X. So the interval for C has to intersect the interval for X. It's pretty clear here that we cannot do that with this class of interval orders. We're going to do a similar process for this 4+1 poset here. We're going to start with the exact same thing that we did before. The forced 3+1, in this case, we're using B, C, D, and X as our 3+1. And now we can put in the intervals for E and F. They're both just allowed to be single points here, so we can put them in without breaking any of our rules. The problem again that you've probably spotted is where can we place A? A must be less than B, strictly less than B, so the entire interval for A must be completely to the left of that single point that is B, but it must also be incomparable to X, so it must intersect X. All right, and it's pretty clear again that there's no way for us to do this with the class of interval orders that we are currently using. So the next steps after going through the proofs of the lemma corollary and theorem is we want to make sure there are no other forbidden configurations. We know the ones we've discovered are forbidden using this class, but we don't know that there's not some bad guy representation out there that we haven't yet found a way to rule out. as a possible representation. To do this, we're working a lot with weighted digraphs, with potential functions, and we're trying to come up with an algorithmic way to, if you're given a poset, determine whether it either has a interval representation using 0, 1 OC interval orders, or whether it contains some small forbidden poset that keeps it from having that interval representation. To do this, we're trying to generalize some of the work done by previous teams. They have algorithms that work for other classes of interval orders, and they use the same strategy of weighted digraphs and potential functions to do so. So we'd like to take their work and sort of broaden it out and generalize it so that not only can we use it to show what we want to show, but also future researchers will be able to use it to prove things for other classes of interval orders. And I'd like to thank everybody for listening to my talk.
Thank you very much, Anthony. All right, does anyone have any questions? If you do, please leave them in the Q&A or the chat. All right, thanks again, Anthony. If there are any questions in the chat, we'll let you know, but we'll go ahead and move on to the final student presentation for this. Last up is Luis Sanchez Mercedes from Rhode Island Beta. Luis, if you want to go ahead and share your screen.
Can you see the presentation?
Yes, I can, and I can hear you.
Okay, so hi, my name is Luis Sanchez Mercedes. I am a applied mathematics and statistics student at Brown University. This is actually my first KME conference. I'm extremely excited and extremely thankful for this opportunity to share my work. Without further ado, this is cryptonomics and empirical analysis of the internal and external performance of blockchain networks, presented by me. To provide you with an outline of the major key points that will be taken within this talk, I will initiate with an introduction of some basic concepts of what constitute a blockchain network and how, in their own manner, they allow for the creation of trust. I will proceed with a very brief description of the objective and how I came about it. Then I will go in depth into the actual design of the study and the models that I took inspiration from. I will proceed with a very brief description of the assumptions that I had to make. And then I will show the result of the model, my interpretation of it, and then how I validated it. And finally, I will give my final remarks and leave the door and leave the room open for questions, basic concepts. I would like to begin my talk with a very simplistic thought experiment. For a moment, I want you to just close your eyes and sort of visualize two people. The first person that I want you to think of is a person that you find yourself having a great sense of trust. This is a person, if we're talking about family, it could be your parents, your siblings. If we're talking about relationship-wise, it could be your spouse or your girlfriend. We're just talking about people in general. It could be your best friend or someone who you find yourself seeing as a mentor. And then I want you to clear your mind again and think of a person that is on the other side of the spectrum, a person that you don't find yourself trusting, a person that you might see as deceitful. This is where the experiment comes into play. Imagine that for a second, both of these persons were to provide you with a very important piece of information. It could be maybe an offer, it could be maybe a statement about the weather. Even though they might provide you with very similar or the same type of information, you would be more inclined to wait for that person that you find yourself having more trust to. And this is very simple, but it's actually a key component within our society. The Palgrave Macmillan Dictionary defines trust as a disposition to rely on another to behave openly, honestly, and transparently toward these fellows. This definition, while very simple in its nature, does a great job of summarizing the idea behind trust. When you trust on someone or something, you're relying that their behavior will not be detrimental to you. And this disposition can be either built through years of experience, years and years of experience that you have with the person at hand or it's the institution that you have, or maybe a recommendation from a person that you already trust. This plays a major role within financial institutions and economy. If you sit down for a second and just think about the structure of financial systems around the world, an overwhelming majority of them are built on the basis of fiat currencies. A fiat currency is a currency that's not backed by anything. The value of them stems from the trust that we have on the system. It is because we believe that the economy works, that the economy actually works. And this is a very powerful idea, but it's also dangerous because it means that the moment that we lose trust in the system at hand, the economy goes into a bust. Thankfully, this hasn't happened to the major financial system, but a lot of underdeveloped economies, when people started not relying on them anymore, started crashing because of this fact. And this is where blockchain essentially comes in. Blockchain, as defined by the Merriam-Webster Dictionary, is a digital database containing information such as record financial transactions that can be simultaneously used, shared within a large decentralized public accessible network. This is a very abstract definition, but essentially what a blockchain does is through the participant on the network. And this idea came about at the moment where we were losing trust in our economy back in 2008 with the introduction of Bitcoin. And it came about because people were turning more away from the economy due to the deceits that a lot of large institutions have and the effect of the financial crisis. What a blockchain does is takes a bulk of transactions transmitted to the network and through these participants and through a consensus algorithm, which I will go define after this, comes into a majority and allows for the build-up of trust. Where trust comes in is again into this consensus algorithm. And a consensus algorithm is just a process in which a computer achieves an agreement across the different groups. I like to think of an analogy as think of a group of consultants, like the nodes on their network, they each, through their own method, find their own way to solve a particular research imposed by the organization. If a majority of the consultant through their own way deduce the same solution, then the action is taken. But if there is a conflict and each has a different solution, then no action is taken and essentially the process is reset again. This is the basic concept of a consensus algorithm, and there are different methods that this is done. Most majorly is the proof of work concept, which relies more on the introduction of a very difficult mathematical problem within the network and essentially making the participant try to solve it and giving the ability to write within the chain to the one who actually gets a solution. In terms of what a blockchain network allows us to obtain, it allows for the creation of an internet of value. Unlike the normal internet that we have at hand, an internet of value is an online space in which individuals can instantaneously transfer value between each other, negating the need of a middleman and third-party costs. We don't often think about it when we're making transactions, but it takes a lot of processing power to, and a lot of backtracking and a lot of dealing with middlemen to actually, for that transaction to go through. What a blockchain allows you to do is cut through this lag by making the participants of the network work to validate the transactions, and we are ensured that on their validity because they're rewarded by the coin and they're putting their computational power within it. And this is now going to the objectives. In terms of cryptocurrencies and blockchain network, if you go into industries there, either you'll find people that finance, oh, this is a revolutionary idea. This is the idea that's gonna buckle down the traditional network that we have. And then you'll find other people who are, oh, this is just not useful at all. This is not it. I am the type of belief I'm kind of in the middle ground. I think it is a great idea, but I think it's missing a few components that can really drive into it. And amongst those components is this notion that I define as a manager. If you break down the financial institute, our financial system, and truly define what you see, what you find, where you find the trust the most, and take them piece by piece. This is a picture of the Federal Reserve, and where our trust really relies is on this centralized figure to do a competent job at managing the currency. And a cryptocurrency does not have this component. And this is where people are essentially free of roam to do whatever they want with the cryptocurrency. And this is where we find illegal activities and pumping up of the prices. And this is a component that I personally think should be added within a blockchain. This is where kind of my abstract comment. The purpose of this talk and the purpose of the research that I did was not to go into the in-depth into the architecture of what this managerial system is. I find that it would take an incredible amount of time and would essentially make this talk even longer than it is. What I mainly focus on was what indicators, both internally within the blockchain system and also externally, affect them, so we can sort of visualize what should a managerial system is and what should it make the decision to manipulating the cryptocurrency at hand. In terms of the design, previous models that I essentially looked for, one of major was the Hayes model, and this model essentially took different metrics like electric costs, market price changes, and essentially the difficulty of the proof of work, which is a consensus algorithm, and try to define an equilibrium price and compare it to the current market price to see what value is being added by the network in comparison to what people believe the price should be. Another model that I heavily got inspired on is this I named it based on the authors, but this took in from the previous model and took in the fact that a blockchain network is composed of each blockchain network separately has different producing machines that are utilized, and this took into effect that efficiency of those machines and the cost that it takes to handle them, and calculated as well an equilibrium price from a cost and a profit, and then compare it against the current price at hand. Both of these models found that the equilibrium price and the current price at hand were running in the same process, and were able to find essentially good prediction from it. In terms of the inspiration that I got in the components that I built on it, the model that I created, I segmented it to 4 different sections. A network section that essentially focus on the day-to-day changes that the cryptocurrencies experiences through its participants and also the changes in transactions. I also focus on the mining, and this is kind of inspired by the 2 previous model, focusing on the cost and the revenue that a node on the system would intake if they were to participate on it. Then there's the market component, and this is more, if you are invested within this cryptocurrency system, how much are you able to gain? And this is the return on investment and the market capitalization of the cryptocurrency at hand. And finally, an economic section, the focus on more external macroeconomic metrics, like the changes in the S&P 500, for instance, the changes in disposable income, the inflation rate among the country at hand. The research questions that I imposed upon myself, the first one was what section, when analyzed together, was the most effective in terms of the changes in price. The next question that I wanted to answer was what section, when analyzed separately, change the least when you move from analyzing it individually to analyze it as a whole, and what specific metric within all the metrics that I analyzed remain largely significant, both from the initial and the final model, and who had the largest changes between the internal metrics, and this is the network activity and the mining, against the external factors like the market, the return on investment, the economic, the inflation. And how does, and the final question that I asked myself was, how does this work within the managerial perspective? Estimating the model. So I looked into four different subjects, and so four different cryptocurrency networks: Bitcoin, Ethereum, Dash, and Litecoin. Each one's different in their own manner, and each one composed of different characteristics. One of the major assumptions that I had to make when making this analysis was that because I couldn't look into other countries and I couldn't get their information, I had to just take in the information here in the United States. I also had to make the assumption that the technology among them did not change incredibly while I was looking through the years. And essentially that there was no big changes among them overall. In terms of the model that I utilize, is again utilizing these specific sections, and then compare them against the log price to measure the percent change in the price. I utilize a panel regression analysis as my framework to taking the fact that they were changing over time and draw a generalized notion from an analysis of the specific section against the price at hand. This is more of the components of what make up these specific sections. And as you can see, the network is composed of different characteristics that change through day to day. The mining section, and this is where, again, comes that previous model that I was talking about. I derive essentially what a node on the network could potentially gain from it if participating. Market, essentially what you would gain from participating within the currency and the economic, the changes within the macroeconomic features at hand. Results. So as described in the other section, this is kind of what just you can see as a result. I segregated each one of the analysis separately, and then did a final model with all of them together. And this was majorly more to find, rather than accuracy, it was more to find which one correlated with the changes in price. And I utilized a fixed model to maintain this. And in terms of the answer to the questions that I had at hand, I found that the section that had the most impact overall, the section was the economic one. In terms of the who changed the least within going from that individual change that you saw in the results to the final model, again, the economic section seemed to perform incredibly well and was significant within the 95% confidence level. This is the metric that I found the most impactful was the interest, the consumer price index, and the disposable income that a person at hand. This plays a entirely a more incredible impact within the changes of price. There's of the internal and external, and this is where I wanted more entrance. What's going on within it, compare against without it. And I found that externally, and this is unsurprisingly, as you can probably would take from just watching last year's results of Bitcoin on, externally, the cryptocurrency had more, the external factors that affect a blockchain network had a more impact than the internal ones overall. In terms of the managerial aspect from it, I found that if it all depends on the perspective that you take at hand. If you're looking at this into a controlling more, making a blockchain controlling more price at hand, this would be a great initial framework because it looks at the different factors and looking at the economic perspective or the external or external one is an important piece to take in. But if you're looking more into like a manager overall, kind of like the Federal Reserve Bank, a much better model would have been a much better a paper would have been to look at other different metrics and then compare and contrasting the sections against them, because the Federal Reserve Bank just doesn't look at the price of the currency, but also looks at other economic factors within the economy overall. Final remarks conclude. This paper started out as an understanding of managerial body. It works through the different topics and the models that were created. It tests out different metrics and try to determine the external price, and then laid out, even though it wasn't the best framework, it's the starting framework that can be utilized as you build the architecture in the model. In terms of the future, I see this managerial perspective would be even more influential now with as more second generation blockchains, which are blockchains that rather than the original one like Bitcoin, it looks more into building an economy through applications within it. So having a managerial feature within it would be even more beneficial because it would manage the application at hand and would even bring even more value to them. In terms of actual events that happen, the Federal Reserve Bank is actually looking into introducing its own cryptocurrency through the combination of the Fed coin. And it started working it last year, but because of the pandemic, it hasn't released a lot of work. But essentially, this is their own cryptocurrencies backed by the US dollar, and they are going to look into it more this year. And I guess that's it in terms of my presentation. Thank you for having me, and I am open for questions.
Thank you very much, Luis. All right, if anyone has any questions, please leave them in the Q&A section, or you can drop them in the chat. While we're waiting to see if we have any questions after this session, we are going to ask everyone to join the Zoom link that I just posted in the chat. We're actually going to do a group photo over Zoom. So once this Zoom call is closed, please join that Zoom link. I've also posted it in all of the rooms in Sakoko. So if you click on those icons, just like you've been doing throughout the day, you will join that call. All right, Luis, I don't see any questions coming through. Don, Brian, or Rhonda, was there anything that y'all wanted to say before we conclude this session?
I'd just like to thank all of the presenters so far. They've been a tremendous variety of topics and very well presented. The one thing I miss with the Zoom setup is that we can't applaud you individually, but we do want to thank you for the presentation so far.
Luis, there was one question dropped in the Q&A. If we want to read more on your work, how can we? Where would be a good location for anyone to read more of your work? Luis, it looks like you're muted.
I don't have it posted yet because it's still a work that I'm progressing on. The best way would be either to message me directly through my email address.
Awesome. Thank you, Luis. Real quick, I'm going to go ahead and share my screen. We are going to be jumping into lunch shortly. If you're looking to find anyone within Sakoko, if you come to the top left corner of the screen, directly below the home button, you can click on the find function, and here you can type someone's name in. So if you're looking to chat with someone over the lunch break, that's a good way to find them. Again, once you're in a room with another individual, you can turn on your camera by coming to the top right-hand corner, selecting this drop-down arrow, turn on your microphone, and turn on your video. All right, thanks again to everyone. I'm going to go ahead and close this call. I will see you in the other Zoom call for the group photo.